Some types of redox reactions can be utilized in analytical studies. For example, the reaction between permanganate and ferrous ions in an acidic medium can be used to determine the amount of ferrous ions in a sample of a substance. One such substance could be a tablet containing an iron supplement. The following titration activity describes how this is done. Ferrous gluconate is sold as an iron supplement for people suffering from iron deficiency. The label on the bottle containing these tablets indicates that each tablet has 37.5 milligrams of elemental iron. To ascertain the validity of the label, a group of students decided to do an analysis of one of the tablets by doing a redox titration. Recall that ferrous ions react with acidified permanganate according to the following equation. According to this balanced equation, 1 mole of permanganate ions is reacting with 5 moles of ferrous ions in an acidic medium to produce 5 moles of ferric ions, 1 mole of manganese 2+ ions, and 4 moles of water. But recall that the pink color of permanganate is changed to colorless manganese 2+ ions, and the light green color of the ferrous ions is changed to light brown ferric ions. To do this, a ferrous gluconate tablet was crushed into a powder and then dissolved in a 100 milliliter volumetric flask to make 100 milliliters of solution. 4 10 milliliter aliquots of this solution were then pipetted out into 4 250 milliliter Erlenmeyer flasks. A 50 milliliter burette was then filled with 0.001 mole per liter acidified potassium permanganate solution. This solution was then titrated with each aliquot of the ferrous gluconate solution until a pink color was obtained that marked the endpoint of the titration. Note that the pink color of the permanganate solution is used as the indicator. When only ferrous ions are just oxidized, any additional drop of permanganate causes the solution to go pink. Of course, this is the titration apparatus. That's the stand, that's the burette there, that's the Erlenmeyer flask with 10 milliliters of the solution, and of course, that's the filled burette there with the permanganate solution. So after titration has been completed, you can see that the solution goes pink. In this case, the permanganate is its own indicator. The following were the results obtained when 10 milliliter aliquots of the ferrous gluconate solution were titrated with 0.001 mole per liter permanganate. Now you're asked to use the information provided in this table here to calculate the mass of the ferrous ions present in each aliquot. We can see in the end, these are the volumes obtained for each titration. So how do we use the information here to calculate the amount of iron in the tablet? And this is a solution. Since the first trial is inconsistent with the others, its result can be discarded. Here you can see this one is not consistent with these, so this result here can be discarded. So the first step is to find the average volume of the permanganate used, and that is equal to 13.5 milliliters. Since each of these use that same volume, its average volume must be 13.5 milliliters. That translates into 0.0135 liter. Now that we know the concentration of the permanganate versus this, we can find the number of moles of permanganate that was used in each trial. And it is found by using this formula, N is equal to C times V, which is this times this. And the number of moles of permanganate in each trial was found to be 1.3 times 10 to the negative 5. And this is the number of moles of permanganate that is required to react with some amount of iron that is present in 10 milliliters of the solution. Inspection of this balanced equation shows that 1 mole of permanganate reacts with 5 moles of iron, and that is repeated here. The next thing is to use the stoichiometric coefficients in the chemical equation to calculate the amount of iron 2 in each 10 milliliter aliquot. So looking at the balanced equation, we see that this is the given reagent and this is the required reagent, and they're reacting in a 1:5 mole ratio. So trying to calculate the amount of iron, we're going to use this equation here, given over required. The given is 1, the required is 5, is equal to that amount there, which we have just calculated for the permanganate over X moles of ferrous ions. So after doing the math, it turns out that the amount of iron in a 10 milliliter aliquot is equal to 6.75 times 10 to the negative 5 mole of ferrous ions. The next thing is to find the number of moles of ferrous ions in 100 milliliters of solution. Why? Because the entire tablet was dissolved in 100 milliliters of solution and only 10 milliliters were analyzed. The number of moles of ferrous ions in 100 milliliters is just 10 times that is found in a 10 milliliter aliquot. So doing the math, we get that is a number of moles of ferrous ions that is found in 100 milliliters of solution. Of course, we have to multiply that amount by 10 before we could have ended up with this. Now that we know the number of moles equal to that, we can utilize this formula to find the mass of iron in that tablet. We know the number of moles, and now we know the molar mass of iron. So the mass will be equal to number of moles times the molar mass, and it turns out to be this value. Translated into milligrams, it becomes 37.7 milligrams. But the label indicated that was the mass of the iron present. How do we account for any differences? One of the problems with this titration is that when the permanganate is added to it, it changes ferrous ions into ferric ions, which impart a slight brownish color to the solution. So it is difficult to see the endpoint clearly when permanganate is added to it. So in most cases, it entails using a few extra drops of permanganate. And that is why if you use more permanganate, these values will get slightly bigger. That value will get slightly bigger. Because of that, this will get slightly bigger. And finally, this mass here will be slightly bigger. And that is why the calculated mass, in this case, is slightly larger than what the label says. Thank you for listening.